So this is the Hamiltonian Station. So remember, Hamiltonian is all about hitting every single vertex exactly once. The difference here between path and a circuit is that a Hamiltonian path just requires we hit every vertex exactly once, whereas a Hamiltonian circuit, we have to hit every path exactly once, plus we have to end where we started. So circuits always end back where they start. That's what makes it a circuit. Best way to determine if a graph has a Hamiltonian circuit, we've got a few different ways we can do it. One is that if it just makes a basic polygon of any type, so any kind of shape where you can just follow along the outside, that's going to have a Hamiltonian circuit. And then shapes within shapes, where the vertices on the inside connect to vertices on the outside, those tend to have Hamiltonian circuits as well. So for instance here, we have a shape within a shape within a shape, and all of them have connections coming out of them. So based on our conjectures, we would expect that there would be a Hamiltonian circuit here. And there is. When you're doing something like this, where you see the shapes within shapes within shapes, it tends to be the best to start outside, kind of head inside. And then I usually go all the way to the inside, go ahead and knock that out, and then go back outside, and work my way from there. Oops, sorry, I didn't want to go that way. What is important is that, right, so I'm going to come back down here so I don't skip over that one. What is important is that you make sure that you hit every vertex exactly once, and you give yourself a spot to get back out. So don't get yourself trapped. You can't really see that on here. Let me grab a different board. So they give us 3 on the outside, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. So you got all that stuff going on the inside. So we just have to make sure we get them all connected using their paths. So from the outside I went in, okay, and then I went in further to hit the inside triangle. So down and then back out. And then I came back out to my pentagon here, or I guess that's a hectagon. So came back out to the outside here, and then went around it. So it had a connection there, there, there. Now I can't go here because that would have taken me back to a vertex I've already been to. So now I'm going to go ahead and go up, come back out, go all the way down. I can cut across because they gave me a spot to come up and back down. Okay, so that's kind of what that looks like. I'll try to draw it again on here. Let me grab a different marker. That might help. Perhaps a different color will work. Alright, so I did from here, in, I went in again. Now there's lots of different ways you could actually go. This is just one particular route. So went back down, came here, came back, and went back. Okay, so the only vertex that I hit twice was the one here on the end, which was where I started from. So that makes a Hamiltonian circuit. Okay, and a circuit should be a closed-in shape. So if you look at it, you can see I have that closed-in shape there. We don't have to use every edge. We just have to use every single vertex. So that's essentially what you're looking for on those when you're trying to find Hamiltonian circuits. Remember the path. Whenever you're doing the path, then you have to, if you're going to do the path, then you don't have to end where you started. I'm sorry. Do make sure that you number it, though. Find a Hamiltonian circuit by numbering the vertices for the graph above and give the path that will be taken. So you can also number the edges. I don't really care, to be honest. This one says number the vertices, but you can number the edges as well. So like I could have done 1, 2, 3, 4, 5, and just label, right, all of the different paths. I know it's kind of hard to read on here. Okay, but make sure you number them so that I can follow it whenever you go to do this on your test. Okay, so same sort of thing here. If I'm going to do it, so the very first thing I look at is to see if I can go around the outside somehow, and then since I've got stuff inside, I need to make sure I leave myself room to come back outside. But if I come here, then I get stuck on those, so that doesn't work out. I could come back here, but then when I get here, then I can't get there. So something like this, I might have to start on the inside and work my way out, so we'll try that. So we can go here and then down and around. Alright, so then here, back up, over, back down. So I could find a path, right, because I covered every vertex exactly once without ever going over, but I did not get a circuit, which is fine because it only asked for a path. So mine would have been 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that would be my path there. So if you find one that is hard to get to and or get out of, my suggestion would be to go and try to start there. So like if there's one that you keep skipping over, no matter what you do, try starting on the one that you keep skipping over. Okay, so that's always a good way to go. So sometimes starting at these inside ones is the best way to go, because you know you can always just go around the outside for those. This one says calculate total weight Hamiltonian circuit. Right, they gave you the circuit. Okay, they gave it to you in bold, so you just calculated the weight. All you had to do was add up those numbers. 302 plus 168 plus 305 plus 500 plus 185. You literally just add those numbers up, whatever you end up with there. Let's see, 607, 1107, 1207, plus 12, 60, 72, 13, 14, 307, 14, 307, 1437, I believe that might be right. Okay, just mathing in my head, I'm not real sure. Here, let me grab an actual calculator. Just because mathing in my head doesn't always work out the way it should. So 14, let's see, so let's add them up. So 302, and 165, and 305, and 185, and 500. Mathing in my head worked out, 1457. Okay? Right, so that's it. So then one way to describe the circuit is DECBAD. Rewrite the same circuit two different ways starting at A. Okay, so they just want you to write the same circuit two different ways. So like I could have gone from A to D. Remember we talked about the fact that those are technically different routes. So A to D, up to E, down to C, up to B, back to A. Make sure that if I'm doing a circuit that the beginning and end are the same letters. I noticed on the quiz that a lot of us would get all the way to B and then not close it out, right? If we're trying to find a circuit, then it should start and end with the exact same letter because we should be ending where we began. Okay, so there's one way to write that. Another way would be to go the opposite way. So even if I started at A again, I could have gone B and then C and then E and then D and then back to A. Same exact Hamiltonian circuit, but because it has a different route, we consider it to be a different one. So two different ways to write that, and that's all they were looking for there. So find three Hamiltonian circuits from vertex A. Mirror images count as different circuits, right? So same sort of idea. We can do them in different directions, right? So Hamiltonian, every vertex circuit, we need to start back, or we need to go back to where we began. So here's one. All right, that's that whole, see if you can just find a shape, right? Any kind of polygon. So there's just a polygon. It just goes around the outside. So there's one way to do that. So it says find three. So there's one, right? So we can go A, B, C, D, E, back to A. Okay, which means I could also go backwards, right? I can just take that same thing and write it backwards. A, E, D, C, B, back to A. All right, there's two of them. So then we need to find one more Hamiltonian circuit. Okay, so just another way of doing the same thing. They still want me to start at vertex A. So I could have gone, let's see, A to B to D to C to E back to A, right? That would work also. So A, B, D, C, E, back to A. Again, start, stop, same point, right? Everything starts and stops at the same point. Then it says find the Hamiltonian path starting at vertex C and ending at vertex E. If it's not possible, give an explanation. Okay, so let's see about that. All right, find a Hamiltonian path starting at C, ending at vertex E. Okay, so finding it starting at C, ending at E. Here we go. So C, If I go up to A, there's no way to get back down, okay? So, there's no way to go back down. Either we skipped D or we get stuck over here, so that doesn't work. So let's try a few different ways. So starting at C, I could have gone D, B, A, E. Find a Hamiltonian path starting at vertex C, ending at vertex E, and we just got one, right? So C, D, B, A, E. We got all of them, okay? But if we were to go back down now, we would end up at D, and that would not work for a circuit, okay? So we got a path, and it starts at C and ends at E, okay? So that would work. Now this bottom one is a weighted graph. Right, the weighted graph at the left represents the number of hours required for traveling salesmen to travel from city to city, which are represented by the vertices. So the cities are our vertices. So A, B, C, D, and E are our vertices. Those are our cities. If he must visit each city and start and stop at city E, all right, so they give us a start and stop. Find the shortest route starting in the traveling time in hours. Give a step-by-step instruction how to complete the tour to justify your answer. So anytime they give me a weighted graph and I know that I want to hit every single line, so find the shortest route starting in travel. He has to visit each city, okay, and start and stop at E. So visit each city, start and stop at E. Find the shortest route starting in traveling time in hours. So lots of ways we can go about this. We know we need to hit every single vertex exactly once, and we know we want to find the fastest way to get there. Okay, so from here, one way to look at it is to try to figure out see if we can use the shortest ones possible. Okay, keep in mind this is not the Eulerizing process because we are not Eulerizing. We don't need to hit every single path, so we just need to worry about hitting every single vertex in the smallest amount possible. Okay, so E, we can go across. This one's the smallest, so I'm going to try to use that. Right, so 2, and then I need to get across to each one of these, so I have to kind of figure out which way is the fastest way to go from here. So from B, I've got an 8, I've got a 6, and I've got an 11. So I'm going to try to use the 6. Okay, from here I've got a 3, I've got a 7, so obviously I'm going to use the 3. Okay, and then I've got a 9, 5, and 4, so let's go up 4. Okay, so then from here, we need to go fastest route back, right? Okay, and then from here, so we could technically backtrack because it doesn't say that we can't, but we do need to get back to E. So from here, we'd have to kind of look at, so I could go 9 here, I could go 9 here, 7 and 10 there, 8 and 6 and 10 there, 8 and 2 there, so 9 seems like the fastest, so we're just going to cut straight back. Okay, so that's looking like the fastest way from there. We'll check a few other ones just to make sure, but that does seem to be the shortest amount, because the only short one we missed was the 5 here, so we'll check it with the 5 in just a second. But remember, we don't want to have any cycles until we actually close in the E. So we've got total time 2, 6, 3, 4, and 9. Okay, so we got 24, 13, 16, 22, 24. So 24 total hours. So let's check and make sure that that is the fastest that we could possibly do. Right, because this is not a network, so we can't just randomly connect. Otherwise, we'd use crucicles, but that's not what we're looking for here, because it's got to be a path, right? Because we have to visit each city. Okay, so sorry, I was reading again. Okay, so let's double check. Let's see if we can go the other way and see if it gets any shorter. So we've got a 5. I've got a 4. From here, I can go 9, 7, or 8, so 7. From here, I need to get to B, right? That's my only option, so that would be across and then back down. Okay, so from here I've got 5, 9, 16, 5 plus 4 plus 7 plus 6 plus 2. That looks like that might be a little faster. 9, 16, 22, 24, exactly the same. Okay, so we have 2 that are exactly the same. In which case either one of them would work, right? We talked about the fact that you can have different paths that have the exact same time. So either way we would get the same spanning time, minimal time, even though we have different vertices. Okay? So that's the gist of the Hamiltonian. The big part about Hamiltonian is, remember that you have to hit every single vertice exactly once, and if it's a circuit, you have to go back to where you started from. If it's a path, you do not. Okay, so be careful with those. Make sure you're paying attention to all the instructions. Make sure you follow everything. So if it doesn't say you have to hit every line, then you don't have to hit every line. If it doesn't say you have to hit every vertice, you don't have to hit every vertice. So you got to listen or pay attention to stuff like that when you read. Okay, so that's Hamiltonian. Oh, the step-by-step instructions. Let me do that part real quick. All right, so if I just wanted to find the step-by-step instructions, the way that I went about it was just to start at E, right, and then find the shortest path out, and then continue to do that. All right, so I would find the shortest path out and then continue to do that from each vertice, as long as it doesn't lead back to a vertice you've already used. Okay, so I went from here, right, on this one, I went from here, and I said, okay, there's 5, and then I went for the shortest. Ooh, I missed the shortest. Let's go back and check that. Let's check my instructions there. Right, because I came here, and I could have gone up 3, so let's see if that makes that any better. See if that changes anything. So 5, could have gone up to 3, and then from there, 6 is still the smallest. I can't go back 2 because that's going to take me back to E already, and we're going to miss C. Can't go back to D, so the shortest path after that would be 8, and then we would have to go back there. Okay, and then 9, and that would be 14, 23, 28. So that got bigger, so that's good. Okay, so find the shortest path. Starting at E, find the shortest path out, and then just work your way around. So, and continue to do that for each vertice. Without going back to a vertex. Okay, so that seemed to work because I followed out the 2. That was the fastest one. That one got me to a minimum time, so that worked out. That's the end of Hamiltonian.